So rewriting ELBO using the property of conditional expectation, rewriting the ELBO using the property of conditional expectation. So we just wrote that particular property, right? Property of conditional expectation. We will have the following. So let us just copy that. Now the third term will be a product of two expectations. Is plus. So we just use this property now, that whatever we have, this expectation, we'll write it as product of these two expectations. Right, and there's also a sum. And we have a sum term here, and this has to be summed over t equal to 2 to capital T. Okay, this is what it is. So why did we write it this way? The first term is okay as is. You can recognize readily that the second term is KL divergence by definition. So expectation of log of ratios of distributions, and this expectation is with respect to one of the constituent distributions, is the definition of KL divergence. The third term, this thing, right, is again KL divergence. Because we wanted to write that as KL divergence, we wrote it as product of two expectations. So now only if you have expectation with respect to one of the denominator distributions here, that you can write this as a KL. So this is equal to, we will write the first term as is. So this is expectation of log of p theta x1 given x0. Sorry, x0 given x1, your pardon. So this is x0 given x1, and this expectation is with respect to q of x1 given x0, and the second term can be recognized as the KL divergence, the negative of KL divergence. This is dKL between q of xt given x0 and p of xt, and the third term that we have is minus, we have an outer expectation with respect to q of xt given x0, and whatever we have inside is again an expectation, a KL divergence. This is the KL divergence dKL between q of xt minus 1 given xt and x0, and p theta of xt minus 1 given xt. Yeah, so that's it. So this is the final expression for the ELBO of a DDPM. So let me just circle it. Okay. So this is the algebra. So the ELBO or the loss term or the lower bound of the log likelihood function that we would optimize for a DDPM contains these three terms. Okay, so let us just write those down. So if you recall, the first two terms are very similar to what we saw in a VAE. Okay, so this looks like the reconstruction given the first latent variable, right? I mean x1. So this is very similar to p theta of x given z, and the expectation is with respect to q of z given x. The only thing is we have taken the first latent variable, right? Here we have hierarchy of latent variables, we are just taking the first latent variable here. The second term here is very similar to q of dKL between q of z given x and p of z. That's exactly what it is, right? Where xt is the tth latent variable and x0 is the data variable. This is also similar to the VAE. but because of the, oh, I think I made a mistake here, there is a sum over all t. Yeah. Because of the hierarchical nature of the VAE, we will have this extra term here, which is actually the most important term, okay, in the training of a DDPM. Okay, the first term, okay, let us write all three terms one by one. So the above objective of DDPM contains three terms. Contain three terms. Let us take them all one by one. The first one is the conditional data likelihood. This is typically the reconstruction term. Right? Why? Because this is trying to reconstruct the data x naught back from the first latent variable. This is the usual reconstruction term that appears in the VAE literature. The second term that we have here, which is the KL divergence between these two, is the prior matching term. Okay, this is called the prior matching term. Why is this? Because it is trying to prior matching term. So this why is this called prior matching term? It because it is trying to match the prior of the latent the tth latent variable to the conditional distribution of the latent given data, okay, which is similar to what we have in the second term of a VAE. So there is this third term which is called, which is this particular sum is called the consistency term or denoising matching term. So this term is called the consistency or denoising matching. Okay, I will tell you why it is called denoising matching term. See that it's called a consistency or a denoising matching term because okay, so I think there is one more bracket that we need here to delineate the KL divergence. This is called the denoising matching term because this distribution, as I have already told you while defining this, can be seen as like known denoising. So denoising is the decoding process, as I said, right? The encoding is called the noising process, and this is the denoising process. So this is known denoising because given x naught and xt, we know what the distribution of xt minus 1 is. So this is a known denoising process. I mean, this corresponds to the known denoising, and this is the learnable or the model, the learnable denoising. So we want the model or the learnable denoising term to match to the known denoising, okay, which the forward process is already imposing. So by minimizing the KL divergence between these two terms, what we are actually doing is we are trying to match the denoising process that we obtain through the defined forward process and what the model is trying to do, and that's why there is a consistency between the two denoising processes, and that's why it's called denoising matching of the consistency term that comes up extra in the DDPM formulation. Okay, now you also notice that the okay, so what do we have to do? So before I come to that, the goal objective has always been to find a theta star, okay, that would maximize the ELBO, right? That is what we have been looking at. So which is j theta of q, which is our ELBO. So we need to take this expression that we have derived and try to find a theta that would maximize this. Now please note that the second term here, which is the prior matching term, can be completely ignored because it is independent of theta. So no matter what model parameters that you take, independent of theta. This is independent of theta, so it can be ignored. Okay. So reconstruction term depends on theta because it has p theta of x naught given x1. So I will come to how to optimize for the reconstruction term because it is pretty easier to do it. So what is interesting and requires a bit of more discussion is how to optimize the denoising matching term or the consistency term with respect to theta. Okay. So what we will do next is write down the consistency term and try to find out how to compute the scale divergence between these two distributions. Okay, that is what we will do. So let us look at computing the consistency term, or rather estimating the scale divergence in the consistency term. So in the ELBO we have the consistency term and that has a scale divergence between these two distributions and that has to be estimated. So let us take these scale divergence and try to estimate it. That is what we are going to do now. So you will be pleasantly surprised to know that despite all this algebra that we are doing, the final expression that we obtain for the consistency term is going to turn out to be very elegant and simple. Okay. This comes from the definitions of the distribution that we have taken. Okay. So we have to compute the scale divergence between these two distributions now. Okay. Now first of all we have to compute the known denoising term. Okay. To compute q of xt minus 1 given xt and x naught, we will have to compute this. Okay. So because scale divergence involves two distributions, right, we will have to compute both of them. Let us take the first one and then we will go to the second one. So what do we know about this distribution? Q of xt minus 1 given xt and x naught, this is equal to, we will just use the Bayes law because we know, see again when we defined this so called known reverse process, okay, we use Bayes law to convert the forward to reverse. Now all the definitions that we have are for the forward process, right. So therefore we will again invert it back to the forward in the forward direction, so that we can use all the definitions that we know of to compute this. So this is q of xt given xt minus 1 and x naught times q of xt given x naught divided by q of xt given x naught. So this is simply the Bayes law, again Bayes rule. Okay. Now we will use the definition of the Markovian process. The first term here can be simply written as q of xt given xt minus 1 because given xt minus 1, q of xt is independent of x naught because of the first order Markov process. So this is q of xt given x naught divided by q of xt given x naught. Oh, what happened? This should be xt minus 1. Yeah, beg your pardon. This is xt minus 1 is q of xt minus 1 given x naught and this is q of xt given x naught. Yes. Okay. Okay, so we need the LHS. We have these three terms in the RHS. Do we know q of xt given xt minus 1? We do, because that is how we have defined the Markov chain. Do we know the other terms in the numerator? Do we know the other terms, the second term here? So q of xt minus 1 given x naught and q of xt given x naught are unknown. Okay. Why? Because, okay, let me write that down. So q of, so we know q of xt given xt minus 1. How? Because by definition, right, we have defined this to be a normal distribution with mean being equal to what was the definition? Was it root of alpha t times xt, and the variance was 1 minus alpha t times the identity, right? This we know, okay. But what about q of x t given x naught, right? We need to compute this to get the LHS here. How do we get? See, it turns out that this can also be obtained. So, this can be obtained using recursion. A simple recursion will give us this particular discussion, this distribution recursion. How is that? Let's do that. So, we have as below. So, we have xt to be equal to root of alpha t times x t minus 1 plus root of 1 minus alpha t times, so let us call this some epsilon t minus 1, where epsilon t minus 1 is again a dummy variable, right? It is simply a sample from normal 0 1. This is our definition of the forward process. This is how we have defined and we know this. Okay. So, let us simply recurse over this. So, to xt, now what I can write is I can write xt minus 1 in terms of its predecessors. So, I will write this as root of alpha t minus 1 times x t minus 2 plus root of 1 minus alpha t minus 1 times epsilon t minus 2 plus 1 minus alpha t times epsilon t minus 1. Okay. Now, what is epsilon t minus 2? It is again another sample from a normal 0 1. Okay. So, you can look into that as an independent sample from normal 0 1, which is identical to epsilon t minus 2. Okay. Now, I will just unroll this. So, this is root of alpha t times, okay, under the root we have both of these. We have root of alpha t into alpha t minus 1 times x t minus 2, and plus we have this weird looking term. So, this is root of alpha t minus alpha t times alpha t minus 1, this multiplied by epsilon t minus 2 plus, you can verify the algebra later, you take it for granted for now. So, this is simply unrolling this off, this times epsilon t minus 1. Okay, this is what we have. So, now let's consider this second term here, okay, and we will see what this is. So, let us name this some t1, okay, or t2. So, now consider t2, that is equal to, just copy this, don't want to write it again. Okay. See, what does this look like? You can simply write this way, right? This looks like some a times some epsilon 1 plus b times some epsilon 2, okay, where epsilon 1 and epsilon 2 are drawn IID from normal 0 1. So, what we are having is a linear combination of two random variables that are drawn IID from. So, epsilon 1 and epsilon 2 are both drawn IID, okay, from normal 0 1. Okay. So, from the property of Gaussian distributions, we know that if you combine two Gaussian random variables with 0 means and unit variance, you are going to get another random variable that is Gaussian with a particular mean and particular variance. Okay. So, what we can show is that, so T2 is a linear combination of two normal random variables, and therefore it will lead to another Gaussian random variable with the following properties. Please verify this. What can be shown is that the T2 will give another random variable equal to some epsilon that is drawn by normal distribution with the 0 mean. The mean does not change, the variance would change. So 1 minus, so because both of these have 0 means, right, by scaling them the mean would not change. So this is 1 minus alpha t into alpha t minus 1 times I. So please, you can verify this, it's very easy to verify that this will give us another random variable that has this particular property. Let's call this some epsilon star. Okay, so plugging back to the expression that we have here, what do we have? We have xt in the LHS. So now xt is equal to root of alpha t times alpha t minus 1 into x t minus 2 plus the second term, which I can represent as another Gaussian random variable, right, which is 1 minus alpha t times alpha t minus 1 times some other epsilon t minus 2, okay, where this, I'll call this epsilon star t minus 2, where epsilon star t minus 2 is again sampled from normal 0 1. So what did I do? See, we had a linear combination of two isotopic Gaussians, that is another Gaussian with a certain mean 0 and variance something. So we know that any Gaussian with 0 mean and some particular variance can be written again in terms of an isotopic Gaussian. So I just, how do you do that? You just take an isotopic Gaussian and scale it with whatever variance it is, because the mean is anyway 0. Okay. Now I did it for the second term. One can recurse this for all the terms, continuing the recursion. Recursion till x naught. You just continue this recursion till x naught. What we get is the following. So we get our xt to be equal to root of alpha t times alpha t minus 1 into alpha 1 into x naught plus root of 1 minus alpha t minus 1 up to alpha 1 times some epsilon, where this epsilon is drawn again from normal 0 1. Okay, so now I can write this as, so xt can be written as root of alpha t bar times x naught plus root of 1 minus alpha t bar times epsilon, where alpha t not xt, alpha t bar is simply the product of all the alphas till t, alpha I. Okay, this is the definition. So which means, so please look at this. Now epsilon, what is epsilon? Epsilon is coming from normal 0 1. So now this entire thing looks like again reparameterization of an isotopic Gaussian, which means that the distribution q of xt given x naught is simply given by, this is again a Gaussian distribution. Why? Because xt, okay, is a linear combination of, or it's not a linear combination, it's a scaled and a shifted version of an isotopic Gaussian, which again is a Gaussian distribution whose mean and variance are given by the scale and the shift. This is distribution on x naught. The mean is given by root of alpha t bar times x naught, and the variance is 1 minus alpha t bar times the identity. Okay, so this simply implies that the very nice and an important property of DDPM, which means that the tth latent can be obtained directly from the data x naught, okay, without having to hop t steps, right, data x naught, without hopping for t steps. That's it, right? Why? See, how do we go to xt from x naught? We start from x naught, add some noise and get to x1, and then add some noise, get to x2 and so on, right? But here what we have shown through recursion is that xt can be directly obtained from x naught without having to hop for t steps. This is one nice property of the forward process. Now, where did we come from? You recall that we wanted to compute the consistency term, okay, and we want to compute the first term in the consistency, that appears in the KL within the consistency term, and that can be written using the Bayes law. And there we got three terms: q of xt given xt minus 1, which we know; q of xt minus 1 given x naught, and q of xt given x naught were not known. We just use recursion to get that. Okay, so finally we have everything that we need to compute q of xt minus 1 given x naught. So let us take that and try to write it down. So this is getting back to consistency term. Getting back to the consistency term. So we simply wanted this particular term to be computed, right? So the consistency term had these things, and now we know all of them. So this is equal to, so we have q of xt given xt minus 1. We know that this is a Gaussian. So we know that this is a Gaussian, right? This is by definition. We know that this is a Gaussian at xt, and the mean is root of alpha t times xt minus 1, and the variance is 1 minus alpha t times I. So we know this distribution. We just found out q of xt given x naught as well. What was this? This was given by the Gaussian distribution xt, and what was the mean? The mean was a root of alpha t bar times x naught. The variance was 1 minus alpha t bar times the identity, right? And similarly one can write q of x t minus 1 given x naught the same way. This is a Gaussian distribution at x t minus 1. The mean is root of alpha t minus alpha bar t minus 1 times x naught. The variance is 1 minus alpha bar t minus 1 times the identity. Okay, so now we know, we have everything that we want to know to get this distribution. So let us write that down. So therefore, which implies that q of x t minus 1 given x t and x naught will take this particular form. We have this is proportional to, I'll just skip the constant, this is proportional to e power, what do we have? We have all of them have like identity as variances, right? So I can write this as x t minus some constant times, because it's a Gaussian distribution, right? So times e power, all of these are Gaussian distributions, minus we have x, I mean the norm of x t minus 1 minus some mean term here, and in the denominator we again have e power x t minus 1 minus some other mean corresponding to that. Okay, I mean the respective distributions, right? Whatever distributions that are there here, right? You just have to take the corresponding means here and plug it in. So this is again equal to or proportional to another Gaussian distribution e power something. So all you need to do is complete the square. Okay, this will be, so note that this is a distribution on xt minus 1, right? So this will be, you can, if you complete the square in terms of xt minus 1, so we have xt minus 1 minus, it will have some mean, let us call that as mu q, okay, and some variance. This is obtained using completing the square via completion of the squaring. Completion of the square method. I will skip this algebra here because it can be found out in any standard monologue or papers. Completion of the square method. Okay, so you can simply plug in all these expressions for these multi variate Gaussian distributions and complete the square in terms of xt minus 1, one would get it. Okay, so now if we do this, what can be shown as that the q of x t minus 1 given xt and x naught, which is the distribution that we have in the consistency term, can be shown to be a Gaussian distribution because it is simply a ratio of multiple Gaussian distributions, right? It is defined on xt minus 1 and it has a mean which is mu q, okay, which it will be a function of xt and x naught, obviously, right, because it is conditioned on xt and x naught, and it has a variance which we will call as sigma q, where, so this is a piece of algebra that I want you to just verify. Okay, it can be easily verified. Mu q, the mean of this particular Gaussian distribution, is given by this particular expression. This is equal to root of alpha t times 1 minus alpha bar t minus 1 into xt. Okay, so please note that these alphas are all scalars, they are just scaling a particular vector element wise. Xt is a vector, plus root of alpha t minus 1 bar into 1 minus alpha t times x naught divided by 1 minus alpha t. So it's very evident to show that this all, we know all of these and everything is computable, right? And we have sigma q is given by, the variance is given by 1 minus alpha t times 1 minus alpha t minus 1 bar divided by 1 minus alpha t bar times the identity. Okay, it is simply, see, all of these are scalars, I am just scaling, so this can actually be written as some sigma q squared times identity. Okay, where the sigma q squared is simply this entire expression, it's a scalar. Okay, this is given by sigma q square. Sigma q square times identity. Okay, so both mu q and sigma q are known, right, and computable. Both mu q and sigma q, and okay, and therefore this q of x t minus 1 given x t and x naught, which is the first distribution that comes up in the consistency term, are computable. Okay, right, because we know what xt is, we know what x naught is, and we know what the other terms is, that the entire thing can be computable. Okay, so with that, what we should do now is that we should write down this definition of KL in the consistency term. Now we know the first term here, the second term is the model distribution, so let us write that down. Now dKL, the consistency term, is simply the KL divergence between q of x t minus 1 given xt and x naught and p theta of xt minus 1 given xt. Okay, we also know that p theta of xt minus 1 given xt, we have modeled this as a Gaussian distribution, right, because we assume that this is also a Markov chain with Gaussian transitions with the mean and the variance computable, right? This we called as mu theta, and the variance. In fact, in practice what is done is only the mean is computed, the variance is kept the constant, it is kept the same as that of q, so that only the mean is computable. This is a design choice that is done in practice. So which implies that the consistency term now will be between this q and so let me just write that down. So this term now will be, now this particular term is equal to, so we know both the distributions, right? Now this is equal to the KL divergence between two Gaussian distributions on the same random variable. So x t minus 1 and we know that the mean is mu q and the variance is sigma q, right? And the second distribution, which is the decoding distribution, also we know is a Gaussian distribution with mean mu theta and the variance sigma q. See, note that the only thing that is to be computed here is mu theta. Okay. So we need to, the next step is that we compute this particular KL divergence, and we know that Gaussian, the KL divergence between two Gaussian distributions is tractable and that can be computed. We will compute what the KL divergence is, and we will finally get the loss function that we would optimize in the DDPM. Okay. So we will do that next.